Welcome to this video, where we will clearly explain the Hadamard and CNOT quantum gates. These are fundamental components in quantum computing. Phase is crucial in quantum computing because quantum states behave like waves. Waves can interfere constructively or destructively. The Pauli Z gate controls this interference and is heavily used in quantum algorithms. The Hadamard gate, or H gate, is one of the most important beginner gates. It creates a superposition, which means the qubit is in two states at once. For example, it turns a zero state into an equal mix of 0 and 1. The Hadamard gate has a specific matrix representation and a quantum circuit symbol. After applying the H gate to a zero state, a measurement gives a 50% chance of reading 0 and a 50% chance of reading 1. Visually, the Hadamard gate transforms a definite state into a superposition. On the Bloch sphere, it rotates the qubit onto the equator. The Hadamard gate is often considered the gateway to quantum advantage. So far, we've covered single qubit gates like Pauli X, Z, and H. Now let's look at two qubit gates, starting with the CNOT gate. These two qubit gates are essential for enabling entanglement. The CNOT gate, or controlled NOT, acts as a controlled flip on two qubits. The rule is simple. If the control qubit is 1, the target qubit flips. If the control qubit is 0, nothing happens. Combining the CNOT and Hadamard gates creates entanglement. Starting with two qubits in the 0 state, applying Hadamard to the first, and then CNOT results in an entangled state. Measuring one qubit instantly affects the other. To summarize, quantum gates like Pauli X, Pauli Z, Hadamard, and CNOT form the basis of quantum circuits. They are used in powerful algorithms like Grover's and Shor's. Unlike classical gates that manipulate bits, quantum gates manipulate probability and phase, which gives quantum computing its power.